Okay, welcome to Robotics 2. What I want to do in today's class is I want to discuss chapter 12, and then I'm gonna discuss project 8. Once again, there are some students who have not turned in project 8 because they have valid excuse. So I won't discuss the solution, but I will show you or kind of tell you how to obtain the solution. So my hope is that I will take you to the point where you know what needs to be done. And if you are interested in doing corrections, I would like to offer you one final chance. So you can turn in project 8 by Thursday. So turn in project 8 with corrections by 4:23, 11:59 p.m. So I would try to discuss the solution. I won't give you the complete solution. I hope that with the hints, I will show you how to implement those GPS.m and sensors.m inside the Simulink environment. And if you still want to go back and change your code, make corrections, and upload the results onto Canvas, you can do that before this Thursday. So Thursday would be the last class, and we are on our way to complete almost the entire textbook. This has been a fantastic class. So in today's class, I'm going to talk about path planning. And something important, this path planning is applicable. This path planning is applicable not only for UAVs, but for UGVs, for UUVs, underwater vehicles, and also collaborative robots. Oh, to answer Borna's question, Project 9 will not be pushed. Project 9 will be due on 23rd. No Project 9 pushing. So Project 9 due on 23rd. 23rd is the last day of class, and ideally it's supposed to be, oh, yeah. So, yeah, okay, I'll post it again. All the material should be uploaded by 4:23. So turning project 8, project 9 by 23, because that is supposed to be the final 9. p.m. We can't have we don't have any submissions or any assignments after the final state. So that is it. So 23rd. Okay. So now I just want to talk about what we have been talking about, just a sort of a higher level. We looked at the unmanned aircraft state estimation. We looked at the autopilot design. We looked at the path following. We looked at the path manager. And now what we want to do is we want to look at path planning. This topic is very complex, and it is mathematical, math intense. But the good news is all the complex algorithms are implemented in MATLAB. So MATLAB is our friend. So we will talk about something called as Voronoi graphs, which is super important when you study topology, which is study of shapes. We will also talk about rapidly expanding trees, RRTs, and all other relevant concepts. But please understand, even though the math and the algorithms may look super complex, I'm not going to ask you to write the algorithms. As a matter of fact, there is no assignment on last 3 chapters. However, there are MATLAB commands, Voronoi and shortest path, that you can use to design a path for a robot. And this is super important topic. For an example, research is being going on in probabilistic path planning, obstacle avoidance, and topological based topology techniques for path determination in robotics. This is a super duper interesting field. So in today's class, I will try to give you theoretical understanding of what this material is. I won't work out an example. What I will do is I will direct you and refer you to MATLAB, and MATLAB has excellent tutorials and commands that will actually do all this heavy lifting for you. So now let's go to the path planning approaches. There are 2 types of path planning approaches. The idea is you want to go from point A to point B. Now this problem, it's simple for humans because we know where point A is, we know where point B is, and we can also see from 1,000 foot if there are any obstacles in between. But now I want you to visualize, if you have a robot, it could be a UAV or it could be a ground robot. For this robot, it is very difficult first to understand where it is, which is the problem of localization. So it needs to know where it is, and then it needs to map the environment. So there is a field of robotics which is called SLAM, simultaneous localization and mapping, wherein the robot is trying to understand where the robot is, what is the current position, and what is in the surrounding. So it's a very interesting topic, and that's an entire area of research. And at the end of today's lesson, I want to give you some future directions. I know most of you are enthusiasts and interested in become roboticists. Unfortunately, I just could teach very little material in Robotics 1 and Robotics 2. You are welcome to take graduate level classes at ASU, but also I would like to show you some of the resources, free resources on Coursera, where you can audit the classes for free. So audit classes for free. And you can take some advanced classes that will help you understand the path planning, probabilistic approach, probabilistic robotics, and so on. So that I will discuss towards the end of the class. So that way, if you want to take some classes over summer, you are welcome to audit these classes, and that will prep you very well when you go to industry or when you go to graduate school or try to find job as a roboticist. So The two path planning approaches, one is called as deliberative. That means that you know the complete world. In other words, you know where the obstacles are. You have an excellent map of the terrain or the area where the robot is going to travel. But as you can understand that having this map a priori is lot of data that needs to be stored. So which means you need a lot of computational power to store, to access, and then based on the UAV, the type of UAV that you have or type of UGV that you are a priori before the mission. This is super important. Before the mission, you are deciding the path. And then UAV only is going to follow that path. But one thing that you want to understand that this can work in a constrained environment, which means when the obstacles are not moving, when the terrain is not changing, this deliberative path planning would work. But many a times it is not the case. The robot has to work in an unknown environment or the environment that is continuously changing. And that is something called as the reactive path planning, wherein the robot has to react to what is going on around the robot. And again, the sensors that robot has prove super important. Based on the sensor data, there is some sort of fusion algorithm and Kalman filtering, some sort of filtering is working that will take the data from the accelerometers, gyroscopes, lidars, then the camera. So think about driverless car. So driverless car uses the deliberative path planning and reactive path planning. For an example, if you use a GPS and if you want to go from location A to location B, you actually program your coordinates and then the GPS finds the path. That is deliberative. If there is construction going on, then probably GPS will give you the path. Now, on the other hand, if you have a driverless car, the car has sensors, lidar, cameras, and it's planning the path in the runtime in a very short period of time. It's kind of looking ahead and it is responding to the dynamic changes in the environment. So that is reactive. Now, in today's class, I'm going to talk about an important, simple but important concept, wherein how do you do deliberative path planning when you have obstacles? And this derives some of its theory from a very well-known field in mathematics called as the graph theory. And we are not going to discuss the graph theory, but I will tell you what is the logic or what is the algorithm. So reactive is like you are giving robots some autonomy to make decisions on the fly. So for an example, all of a sudden, if there is an obstacle, the robot either would stop completely or try to avoid the obstacle. Or all of a sudden, if there is construction, then there is some real-time changes in the direction or orientation a robot can make. If there is a bird in the flight path, then the robot would avoid the bird, something like that. Now, first and foremost, what do we mean by Voronoi graphs? This is a very simple technique based on creating some graphs and finding the optimal path, at the same time avoiding obstacles. Now, what I want to tell you is think about it. This problem can be stated as this. So we have some sort of a world, and in that world, we want to go from point A to point B. And globally, there are 1, 2, 3, 4, 5 obstacles. And now what I want to do is, this is my start position, this is my end position. So how do I go from start to end? One possible option is avoid all the obstacles altogether. The second option is go somewhere from here. The third option is maybe go from here. Fourth option is maybe go from here. The fifth option is something like this. And this is easy for us, but how do I write a computer program or a software program that kind of gives me the best possible path that the robot can take? And once that path is determined, what I know is I know the waypoint. So I know these sequential points, and I can program the autopilot to go from first waypoint to second waypoint to third waypoint, all the way till I reach the end position. Now, the logic is, first and foremost, I want to divide this region into some sort of segments. First and foremost, how do I divide this region into segments? And in the terms of mathematics, it's basically called as dividing the plane into convex cells. And these cells, each cell would contain one obstacle. And the first case is each obstacle is a point obstacle. That means it is indicated as a point. It's just a location. So the UAV should not go to that particular X and Y location. That's it. So now what is done is, what we do is a very interesting approach. And this approach is, we are going to divide this region into the cells. And these cells are something like this. First, I'm going to draw a line connecting two obstacles. Then I'm going to draw a line which is a perpendicular bisector to this obstacle. So I'm going to draw a line which is perpendicular bisector to this obstacle. Then I'm going to join another line between these two obstacles and draw a line which is perpendicular bisector. So this line is not only perpendicular, but this is bisecting. Then I'm going to draw this line, and again, I will create a perpendicular bisector. Same thing over here. So I'm going to construct one line and create sort of a perpendicular bisector. Same thing here. And then I'm going to create a perpendicular bisector. And the location where these perpendicular bisectors meet, and observe this very carefully. So this is my first perpendicular bisector that is coinciding with this second perpendicular bisector that is along with the third perpendicular bisector. So if you look at this cell, cell 1, there is only one obstacle. This is cell 2, there is one obstacle. And once I repeat this process for all these guys, then I get a shape which is something like this. So which means now I have each obstacle, one obstacle per se. So basically, and as you can see, the edges of graphs are perpendicular, and this edges will maximize the distance from the point obstacle. This is the first step in creating this Voronoi graph. Now the next question is, Good, we got this Voronoi graphs. What is next? The next thing is we will implement our start and end location. So I just want to give you a simple example. In this particular graph, there are 20 point obstacles, 20 point obstacles. And then with the MATLAB command Voronoi, and I would encourage you to look at this MATLAB command Voronoi. What you can do is you can construct this graph, and the complex algorithm that is used to generate the Voronoi graph. And there are different algorithms that generate these graphs, and they have their computational complexity and the amount of time depending upon how those algorithms are implemented. But understand there is a built-in algorithm that would generate this particular figure, wherein what it will do is each obstacle will be in one cell. So that unique cell will have each obstacle. Then next thing is we add start and end point. So for an example, this is the start point and this is the end point. So in the Voronoi graph, we add start and end point. Now what we want to do is we want to find out a path from start to end. How is it done mathematically? To be honest with you, at this point, we need to come up with some sort of criteria. Do we want this path to be the shortest path? Do we want this path that is not near any obstacle? Or do we want this path to be like the path that will be at maximum speed the UAV can travel without any changes? So there are these additional constraints that will give you some sort of cost. So the first step is from this path, you want to connect to the nearest endpoints. So for an example, if you look at this graph, if you are over here, say for an example, this is your start. And what you are going to do is you are going to look at the 3 nearest vertices or endpoints. So that is the first step. And then what you do is you come up with some sort of a cost function for the path. Now this next slide is going to have some math, but I'll tell you what this math is about. So if you think about this point P, and if you think about this edge that is joining V1 and V2, these are the nodes that we identified. So for an example, these are the nodes. So this is a node and this is another node. So you have this point. The distance from this point is given in terms of this function D, 2 nodes V1, V2 and P. So provide this function with the location of V1 and V2 and location of P, and that gives you the relative distance. Now we know what is the length. Since V1 coordinate and V2 coordinate are known, I can find out the length as x1 minus x0 square plus y1 minus y0 square plus z1 minus z0 square. And now if you want to follow the motion of the UAV on this particular segment or on this particular line, this can be given in terms of endpoint coordinates V1 and V2. So think about it. Sigma is if sigma is equal to 0, that means you are at V1. Just imagine, substitute sigma is equal to 0. That shows you W of 0 is equal to V1. If you substitute sigma is equal to 1, That means you are at location V2. And what we want to do is we want to come up with some sort of a distance criteria, which is given as this. That is the minimum of absolute value of P minus W of sigma. And once you do this math, you would realize that you are gonna get a optimal function. You are gonna get certain value of sigma. You'll find certain value of sigma, and that will tell you the location along the edge. This is the edge. Location along the edge when this D value is minimum. And then what you can do is you can find out the value or the distance between the point set Q, which is the obstacle, and the line segment by this function. So what that means is this is giving you some sort of a cost that you want to minimize so that you can decide which path I want to take. So moving on, what you do is you define a cost function which is dependent on the length of the edge and distance, reciprocal of the distance to the closest point. And please note, these cost functions will be different for different criteria. If you want shortest time path, the cost function is going to be different. If you want the shortest path, then the cost function is going to be different, and so on. So these, you will define certain cost functions, and then you run through something called as an optimization routine, to find out the optimal path. And if you don't know anything about optimization, think about it. It's numerically setting the first derivative of the function is equal to 0. But rather than doing it analytically, it is doing this derivative and setting up derivative is equal to 0 numerically. And the algorithm that does this is given in this table, algorithm 9. And depending upon what you want to do, there are different algorithms. A very common algorithm is Dijkstra's algorithm. This is the algorithm that is commonly used, and this is implemented in MATLAB with the command shortest path. So if you want to create a path, a very simple path in the presence of obstacles, step 1 is to create the Voronoi graph using the MATLAB command Voronoi. And the second is supply the initial and the final points, and then use the command shortest path, and that will implement the Dijkstra's algorithm and give you the path. And if you look at the MATLAB webinar on path planning, or if you just go to Voronoi webinar, it talks about how to implement that for autonomous cars. So here is a simple example wherein the first and foremost, what you do is you define the X and Y coordinates of obstacles. Then what you do is you specify the world, which means that what are the X max. This is your X max. This is your X min. This is your Y min and Y max. And then ask Voronoi command to create the Voronoi graph. Once the graph is created, you can actually initialize start and end points, and then use the command shortest path, and this will give you the path along the edges, so that the obstacles are avoided. please note, this is deliberative path planning, which means these obstacles are not moving. And as a programmer or as a designer, you know the world and you know exactly where these obstacles are, and you know where the UAV is going to start and where it's going to end. Now, this can be extended when you have non-point obstacles. And this is a very common problem. So for an example, you just don't want to avoid a particular pixel, or you don't want to avoid this particular point, but you want to avoid this entire region around it. So there are these finite size obstacles, and they don't have to be rectangular, they can be circular. So what we want to do is, how do we manage, or how do we have our UAV travel at the same time avoiding this big region? And again, the argument is, you place nodes at the edge of the obstacles. So what you do is, you insert points or nodes around the perimeters of the obstacles, and then implement the Voronoi function. And then what you do is, you construct a Voronoi graph. And the Voronoi graph, when it is constructed, it does not know as an obstacle. What it knows that it will construct the cells with these points, 1 point per cell. So when the Voronoi graph is constructed, for an example, just consider that each node, this is constructed as a point obstacle that will be in each cell. However, as you notice, these paths will be constructed. So, but clearly, these are not feasible paths. These are not feasible paths because they are going inside the obstacle. And the reason for that is, you want to make sure that your UAV does not hit the obstacle. So what you do is, you construct the path that avoids or that goes through the obstacle. So now, once you start eliminating the path that goes through the obstacle or ends at the obstacle. So I just want to give you an example. If you start looking at this path, this is clearly not a feasible path because it is hitting the obstacle. This is also not a visible path or feasible path. So what happens eventually is, this is the path that I want to take. Then I will go forward, and then I will say, this is the path that I want to take. Then I will go forward, and then I'll say, this is the path I want to take. And gradually, by the process of elimination, that you will come up with this path. And that is how the path is constructed. And then if you go forward, again, this, you don't have to do it or implement this algorithm. MATLAB already has an algorithm implemented for non-point obstacles. So you are welcome to just use the MATLAB built-in function for non-point obstacles, and it will show you the feasible path. Any questions at this point? Just to give, so that just I'm clear, project 8 and project 9 are due with corrections by 4/23, and 4/23 is this Friday, 11:59 p.m. So if you have done project 8, but at the end of today's lesson, if you see that there are some issues that you can solve or improve your solution or make some corrections, you are welcome to do it and turn it in by 4/23. Now the next part is talking about the rapidly exploring random trees. And this is sort of an exploration algorithm. And this is also based on something called as the tree structure. So you have a root, and then just like you have branches, you have different branches. So the idea is you start with a tree structure, expand this tree, and then finally use the path that gives you the minimum cost. Again, RRT algorithm is implemented in MATLAB. I will just tell you how this algorithm works. But if you want to see the algorithm working in action, I'm going to refer you to the webinar, the link to the webinar that are on the Canvas website. So this is, as the word says, it is rapidly exploring random trees, RRT. It's an exploration algorithm that is actually uniformly searches the world. So for an example, this is the world that you are looking at, and you have obstacles. So you are going to start somewhere at a random location, or you are going to start, and then you are going to propagate your path in multiple ways. And at the end, you are going to evaluate under the constraint what is the best possible path. Now, the advantage of RRT is, even though it may look sort of confusing, or how does a random tree give you a good path? And the reason for saying that is you have tremendous amount of computational power available. So computationally, no, it is not reactive. It is deliberative, because the obstacles are, I mean, at least for this discussion, we are considering the obstacles are fixed. They are not moving. It's a constrained environment. So if you have vehicles with complicated and nonlinear dynamics, the RRT can be used for path planning. Now, it can generate one single path, or it can generate multiple paths, and then you can decide which is the best path that you can use. And again, if you look at the way these path planning algorithms work, they use something called as a tree data structure. So this is a data structure. So tree is sort of a graph. This is again the roots of this algorithm are inside the graph theory. So what happens is you start with the root, and then what you have is you have a child node. So this is child node, and then you have a parent node. And then what you do is you have these connections. So every node has one parent except the root node. So the root node is sort of a genesis block. This is where the everything starts. And then certain costs are assigned to the path. And believe it or not, if you were to play the chess against the computer, this is exactly how the computer decides which move to make. So it will go under the certain, so at particular move, computer will construct the tree structure. It will assign the cost to each path, and then finally find out the best possible path, best possible move in the current situation. So if you look at a chess engine, the chess engines typically have these types of structures. Now, how does an RRT algorithm work? So let's start with this world that is expressed as this block, a rectangular block. And then we have obstacles. And these obstacles are fixed. They are not moving. So this is not a reactive algorithm. This is deliberative. And now we want to start at location PE. PS. This is the start location. And we want to end at location PE. That is the end location. So I want to construct a path that goes from S to E. So how do I do that? I'm gonna start with some random configuration. What do I mean by random configuration? Some point P. This point P could be here, this point P could be here, this point P could be here, this point P could be here. And then what I'm gonna do is I'm gonna construct a configuration distance from start point to the next point P. And then I will check this segment for collision. So for an example, if I construct, if my P is over here, and if I decide to construct a path, I know that as I go to this particular location, or for that matter, this particular location, I have a collision. So I will avoid that direction. So what I'm gonna do is I'm gonna construct I'm gonna start with bunch of points and then start following the potential feasible directions. And as I proceed, I will start constructing the path. So what it happens is you actually scan the entire workspace or entire world. You randomly select points, then start moving in those directions. You wait to make sure that there is no collision. And as you can see, you can have multiple paths propagating at the same time. You don't have to have just one path. So you could have one path propagating here. You can have one path propagating here. You can have one path propagating here. And then what happens is you continuously, the algorithm continuously starts adding nodes and checks for collision. So as you can see here, that from this start point, the algorithm adds one path, second path, and then it continuously starts branching out. So this looks like sort of it is branching out. And at the end, as soon as the last node hits the end point or PE, then what you do is you close that loop or you close that algorithm and find the optimal path based on the cost function that you decide. And if you want to look at the algorithm, this is the algorithm, and this is how the algorithm works. You are welcome to take a look at it, but I would strongly recommend to use MATLAB. MATLAB has the function to plot RRT. It can do RRT. And as you can see, it's sort of a random algorithm in a sense that it's picking up points randomly and propagating all those points. And at the end, trying to come up with a path that is most likely the best possible path. It takes a lot of time. So sometimes if you once you construct the path, there could be some inherent constraints that the UAV cannot take the sharp turns, or UAV cannot go beyond certain heading angle. So what you can do is you can do some sort of smoothing. Yes, we don't go back. We basically follow the alternate path. So if RRT reaches to a dead end, then basically that path or that branch will not be propagated, but just like other branch will be propagated. So think about a tree, and all of a sudden one tree branch hits a wall and that branch cannot grow. But instead of, so tree grows in other branches. So, and then at the end, what happens is there is some sort of path smoothing algorithm. So you have these nodes and then you perform the smoothing operation to make sure that the connections are optimal. So for an example, rather than constructing the path from this point to this point, if you can directly go to the third point, then point number 2 or node number 2 is eliminated. And again, there are algorithms for path smoothing, and this is one algorithm, and you are welcome to take a look at MATLAB algorithm, smooth RRT. and then that will actually smoothen out the RRT. And I would encourage you to take a look at RRT star algorithms. So there are very many path planning algorithms. So here is how a typical RRT plot would look like inside the MATLAB. So what you do is you have these obstacles, you have the start point, you have the end point, and you first construct this tree that is shown in the green, and at the end you find that one branch, end of one branch hits the end point, and then with that a path is constructed, and then you run the smoothing algorithm. So this is the path, initial path that is constructed with RRT, and then you run the smoothing algorithm, and then it gives you sort of a smooth path from start to end point. Here are additional results. And please note, RRT can give you one path, RRT can give you multiple paths, and you can, out of those multiple paths, you can choose which path you can use. And here are RRTs used in different implementation. There is something called as RRT star, which is an improvement on computational improvement on RRT. I would encourage you to take a look at that as well. So if you look at RRT star algorithm, the idea is what you do is you are extending the step. Instead of finding the closest step, closest node, it will find all the nodes in the neighborhood. So it will try to look at all the neighborhoods, all the nodes in the particular neighborhood, and then propagate the algorithm. And the idea with RRT star algorithm is it works quicker. It is faster than just baseline RRT. And then at the end, what you are going to do is you will look at the nodes, you will have some distance constraint, and then you can actually reroute, and then you can remove the edges. So if you look at the RRT versus RRT star, I want you to note that this is RRT and RRT star. You can see RRT star is more efficient than RRT. In other words, if you were to run RRT star, you will find the path quicker compared to RRT. And here is an example of RRT versus RRT star. RRT versus RRT star example, in the case of the obstacles that are non-point constraints. So for example, if you have rectangular obstacles, then RRT star can give you the solution much quicker. And the next few slides are not directly related to the material in the textbook, but they are related to the material that the authors performed. For example, you can use the RRT path planning over 3D terrain, wherein you want UAV to fly through a particular complex mountain range. Then you can come up with a particular path, and that path can be in 3 dimensions rather than the 2-dimension path that we just talked about. And here is an algorithm where you can have either a constant altitude, or you can have the variation in the altitude or stepwise altitude, and then you can implement these RRT algorithms in 3-dimensional terrain. Again, path planning itself is a very complex topic, and people, researchers, work on it for their entire lifetime designing the path. So it's not possible to cover the path planning in sufficient depth in just one lesson. But please understand, if you know how RRT works, how Voronoi works, shortest path, and how it can be achieved using MATLAB, then you will be able to implement those algorithms for different types of robot, not just UAVs, but with UGVs and UUVs. The last point that is to be discussed is, can you combine RRT with Dubins? So remember, the Dubins is circular, straight, circular path. And then what you can do is you can actually construct a Dubins path using RRT. And the algorithm for that is you start with a northeast position, find the closest node, then find the distance, and then define the course angle. So if you were to do that, and if you have your UAV, RRT star is quicker. RRT star is quicker and computationally efficient. So if you want to construct a Dubins path using RRT approach, now please note this is a Dubins path. The red path is showing the Dubins, wherein you have curve, straight line, and curve, that type of path. So observe curve, straight line, and curve. This is the Dubins path. So you can combine RRT approach with Dubins. And here are some results that authors have provided in three-dimensional environment. So again, these plots are generated using MATLAB, and MATLAB has a function that can be used to generate RRT and Dubins. So you can generate a Dubin path using rapidly exploring random trees. The last part I just want to touch upon briefly is if you have a surveillance operation, which means you want your UAV to cover certain area, or say if you want to spray your crop, the easiest way is you can have your UAV follow a certain path, or you can have your UAV follow the zigzag path. So what is the best possible path that would achieve the maximum coverage with shortest path, or least amount of time, or minimum fuel consumption? That is an interesting problem in path planning. So idea here is not to go from point A to point B, but you are given a region, and what I want to do is I want to come up with particular path for this UAV so that this entire region is covered either in the shortest the path, or least fuel consumption, or the fastest way to cover the entire path. So there are different coverage algorithms. So what typically you have something called as the terrain map that is used to detect the collisions, and you have the coverage map, which is to track the coverage. And many a times, if there is a return to base function, there is a return path or return map, so that the UAV can go from point where it is to the start position. And sometimes that is implemented if your battery drops down beyond, say, 15% or 20%, and then automatically it can return to the base. So you can implement something like that. And what you do is basically it's sort of a look ahead algorithm, again based on the tree structure. So you have tree, you have nodes, and you have branches. And what you do is you start exploring the tree based on first either uniform branching or RRT. And depending upon what approach you choose, if you use uniform branching, you can say depth first, breadth first, or you can look at the separation, and you can come up with the algorithm that will make sure that this tree or the UAV spans this entire area using this tree with some sort of look ahead approach. And this is the algorithm for coverage. Again, there's a MATLAB function for this, and I would encourage you to take a look at it. The function will need the basic map of the world, so which locations to be covered, and then it will generate the tree, and it will generate the path. And here are some examples based on the algorithm. It will generate the path. in 2 dimensions, it can be extended to 3 dimensions, and you can add additional iterations, and that will refine the type of path that is constructed. And if basically, if you have congested environment, something like this is super important, because what you can do is you can add the coverage, and also you can add some sort of obstacle avoidance. So again, I would encourage you to take a look at the webinar, MATLAB webinar. The links are uploaded on Canvas, and see the practical implementation of these algorithms. In this class, we just talked about the theory, but I would strongly encourage you to look at the practical implementations. Now, what I want to do is I want to show you some online resources if you want to take this knowledge of robotics and build upon it. And then I will show you how would project 8 how can be implemented, and you are welcome to look at or welcome to turn in your corrections. But before I switch my screen, any questions? If there are no questions, yes, RRT takes a lot of storage memory, but there are techniques for optimization. For an example, as soon as one branch is dead, that path is removed from the memory. So there are a lot of tricks that can be used to make RRT efficient. Right, but basically you would need a different type of data structure. So memory requirements for something like RRT or particle filters that use the sort of randomness approach, they are quite huge. So you can start recording, but how big of an array would you record? And then if your array is very, very big, think about an array that is 1 gig in size. To access that array or to process that array, the software will need time. It will take time just to go through the iteration. Think about a matrix that has 1 million by 1 million entries. So it's difficult. All right, now what I want to do is I want to share my screen. And first and foremost, I want to show you some online resources. So Coursera, there are lots of free courses in robotics. For an example, machine learning. If you want to see robotics, so there is this course. This is actually robotics 1. Whatever we studied in robotics 1 is covered in this class: modern robotics, mechanics, planning and control. Then there is this aerial robotics course by University of Pennsylvania. And again, you can enroll for free and audit without paying any tuition. If you look at the robotics specialization, you can take aerial robotics class, and what we studied in today's class and last class is actually computational motion planning, which talks about the graph-based techniques, search A-star algorithms, and all about path planning, RRT, and all the interesting stuff. So if you are interested in finding out more, I would certainly encourage you to take a look at computational motion planning course that is available at Coursera. Then if you are interested in perceptions or probabilistic robotics, this is a good class, robotics perception. If you are interested in bipeds, walking robots, robot mobility, is a good class. If you are interested in more into Kalman filter, particle filter estimation, and how can we make robots learn, this is robotics estimation and learning class. And I would encourage you to look at the robotics classes at Coursera. And please, once again, you can audit these classes for free. So you don't have to pay the tuition, but you can actually learn from professors from Georgia Tech, Stanford, and University of Pennsylvania. So Google, and then you will see tons and tons of classes on robotics. You will see self-driving cars. If you are interested in robotics using Arduino, this is the class. Then if you are interested in reinforcement learning, this is the class. And there are lots and lots of classes, and you don't have to pay for it. And if you look at, there is ASU AI and machine learning certificate. If you are interested in knowing more about it, you are welcome to take a look at the certificates that are offered by ASU. And these are fantastic resources that you should use to further your knowledge in robotics. So now, yeah, so there is a ROS class, robotics. So if you are interested in learning ROS, there is a beginner ROS class, and there is an advanced ROS class. So this is the class that I would recommend just to get familiar with ROS. But if you are interested in knowing more, then there are tons and tons of classes on robot operating system. So I would encourage you to look at robot operating system. So I would encourage you to take a look at, and there is with Python, then neural network. So you are welcome to take a look at these classes. And all these classes have the basic material, the reviews, feedback from students. So you are welcome to select a course that fits with your background and that can be used to enhance your knowledge. Okay, now I'm going to give you some hints on project 8. First and foremost, what I want to show you, the project 8 needs to be done along with some sort of derivative simulation. So either you can use the trim simulation, which we did earlier, or we can use the derivative simulation. So I'm sure all of you have successfully finished this project. And these Simulink files are available on Canvas. Here is the basic idea. You have the derivatives.1 function that is integrated and that is giving you some output. You have force moments function that is giving certain output. And if you recollect, when we run this, we see all these outputs in these scopes. So this is the scope where we see the outputs of the sensors. This is the scope where we see the outputs of forces. And this is the scope where we see the output of the UAV states. And if you want to see the simulation, clearly we have this MAV simulation that is flying the plane. Now what we need to do is we need to interface our GPS.m and sensors.m with this simulation. So what you do is, first and foremost, you have these parameters that are given to you. What are these parameters? The first parameter is the gyro sigma, which is the standard deviation. then the bias of gyro X in X direction, bias in Y direction, bias of gyro in Z direction. You have sigma, standard deviation of the accelerometer. You have standard deviation of the static pressure, and you have the standard deviation of the differential pressure. For the GPS, you have something similar. For GPS, you have the time sample rate for GPS, 1 Hertz. Then you have beta GPS, which is the parameter. You have the sigma north GPS, sigma east GPS, sigma height GPS, ground speed GPS, and sigma course GPS. So these sensor parameters need to be used in sensors.m. These GPS parameters should be used in GPS.m. So how do we do that? Go to sensors.m. In sensors.m, these are the different states. I just modified this file in such a way that it is directly accessing the values for the gyro properties. So these are the states. It has all the way 24 states. First state is north position, east position, down position, U, velocity in X, velocity in Y, velocity in Z. Then you have phi, theta, and so. So you have roll, pitch, yaw, and then you have the gyro body rates, P, Q, R, X, Y, Z. And then from your force and moment block, you have force in X direction, force in Y direction, force in Z direction, moment along X, moment along Y, moment along Z. You have VA, which is the airspeed that you are getting as an output. You have alpha value that you are getting as an output, which is the angle of attack. You have the beta value, which is the side slip. And you have the wind, WN, WE, WD. So I just want to go back to your Simulink file, and please note all these variables that are listed over here. For example, these first 12 variables are available here. This scope block is outputting the first 12 variables. If you look at these forces and moments, this forces and moment block is giving you, all these outputs. So double click on this and note you have force in the X direction, force in the Y direction, force in the Z direction, moments, and then you have VA, alpha, beta, and wind N, wind E, wind D. So all these are available here. So what we need to do is we need to take this output, add this output, and feed that to this sensors.m block. So take the output of this scope, and feed to this user-defined function. So what you will do is inside your Simulink, I'm not going to give you the solution. What you will do is you will go to library browser, and then you will do the user-defined functions. And then what you will have is you will have a MATLAB function. And in this MATLAB function, you will double click and you will have your sensors.m function. In your MATLAB function. So your function will be UU, and at the end, you will have U, or you can just say Y. And you can say save. And once this is saved, you can double click on your function block. You need to save this again. You double click on function block, and then please note you need to connect UU. That UU is going to be combination of input from here and input from here. That is what you will feed to your sensors block. Same thing, you will go back again, library browser, create one more function, double click this function, and in this function, you will have this gps.m. Copy your MATLAB function 3. This is where you will have paste, and you'll make it UU. And then at the end, you will have y is equal to GPS. Save. And however, one thing I want you to understand, that this GPS function will need VA, WN, PN, PE, PD, Psi, and T. So VA, WN, WE come from the force block. So these three parameters would come from here. And these parameters PN, PE, PD, Psi will come from here. And this last parameter, which is time, T, will come from this timing block. And what you need to do is just arrange these signals in sequence, feed those, and at the end, what you do is you will add some sort of a scope over here that will show you the sensor output. But please understand, this is your sensor function. This is your GPS function. So you would connect your inputs. You'll select appropriate outputs from your state and force, and then connect these to your sensors and GPS. So are there any questions at this point? So if you want to go back and revise your code, you are welcome to revise your project 8 and upload it onto Canvas by 23rd midnight. Any questions? Any questions from anyone? If there are no questions, I am going to stop here. And in next class, I would give you an overview of chapter 13. And then you are welcome to follow with Coursera courses and do the webinars that are posted on Canvas.